Hello, everybody. And today is the first lecture. So let's get started. Let me share my screen and we'll have the PowerPoint up just like would be in class. So having said that, let's move this over. What is computer science? Well, a lot of people think of computer science as just writing programs, programming computers, working with computers. But really, computer science is basically using computers as a tool. So computer science or computer scientists use computers as tools. And so what is it that we want to do? Well, I don't know. I do know. Let's see. What is it that we want to do? Well, in reality, we tend to solve problems. Problems are what need to be solved. We have to have a solution. I want to do some arithmetic with numbers. So, and I don't want to do it by hand. So the problem or the computer scientist has to come up with a way to do it not by hand. So we have a little calculator program, right? That's what gets produced. Now, computer science is not just about programming, like I said. Computer science is about all kinds of things, and we'll talk about where they're used in various fields of computer science a little bit later. So what I want to focus on right now is computer science is what we call, or the main part of computer science is computational problem solving. So what is computational problem solving? Well, problem solving, let's just take a look at problem solving in and of itself. For instance, if I needed to solve a problem like, why doesn't this light work when I turn it on? I mean, it does, but why doesn't it turn on? So what do? Well, we think logically. And what we do is we go through some steps to solve the problem. It's natural to divide this into steps. So what am I going to do? I'm going to, I don't know, check to see whether the light is plugged in. That could cause it not to turn on. I could check to see whether the light bulb is burned out. And then how do I check to see whether the light bulb's burned out? Well, I take this one out, and if it's an old-fashioned one, you used to wiggle it next to your ear, and if you heard something, it was burned out. With modern LED light bulbs or the fluorescent kind, we can just get a light bulb that we know that works and put it into the lamp and see if that works. Then we know, hey, the light bulb is burned out. What else can we do? Well, what if I have a light bulb that works and I put it into this lamp and it doesn't work and the lamp is plugged in? Well, now I have to come up with more steps. What is logical? What's the next thing that I could do? Is it the lamp that's broken? So there's something defective with the lamp itself? Or is there no electricity getting to the socket? So I kind of have a choice, and I have to weigh which one is easier, which step is easier to do. So defective lamp. I guess they're both kind of the same as far as difficulty goes. So I could check the electricity coming out of the wall. How would I do that? I get another lamp or something else that I know works, and I plug it into this socket. And if it works, I know that the socket is providing electricity, so it's not the socket. It must be the lamp. The other way is to take the lamp to a socket that I know that is good, that has electricity coming out of it, plug it in, and with a known good light bulb that works, turn it on. And if it doesn't turn on, then I know there's something wrong with the lamp itself. And we can keep going down that to try to figure out why the lamp doesn't work, although that might be a different set of problem-solving steps. So, having said that, what is computational problem solving? Well, computational problem solving is using a computer or computers to solve a particular problem. Computers are good at solving problems because they can repeat steps over and over again. And they don't make mistakes. So for instance, if I add 5 plus 3, a computer will always come up with the answer 8. Always. And if I add the same numbers together a million times, I will get the same answer a million times. So computers are reliable. They have what we call repeatability, which means they will not make a mistake no matter how many times they have to do something. So for instance, if I give you a column of 50 numbers and I have you add it up, well, some of it by hand on a piece of paper with a pencil, right? And you have 50, say, 5-digit numbers, and you have to add those up. Most of you will get the right answer. A computer, on the other hand, will always get the correct answer. Now, if I jumble those same numbers and I give you 10 columns of 56-digit numbers, and you don't know that they're all the same numbers, they're just in a different order, what'll end up happening is some of us will, get the right answer, get the right answer, get the wrong answer, get the right answer, get the wrong answer. So basically what we are doing is we're repeating the same process, but we're getting different answers every time. Why? Because human beings make mistakes. I carry a 4 instead of a 5. A computer, on the other hand, I could give those same numbers to a million times. It would always come up with the same answer, and that answer would always be correct. The only time computers really make mistakes is when the programmer didn't program it correctly, and so then we have what we call logic errors. So where mistakes can creep in. But we try to fix those before we release programs. So that's basically using computers to solve a problem is what computer science is all about. And problem solving is a major part of life. So, I gotta click here. Oops. So, what kinds of computer-related fields are there? Well, surprisingly, there's a lot of computer, or how do I put this? Computers have been integrated into all kinds of things. So, for instance, one of the first places where it came into be, where it was adopted was in what we call drafting or architecture. And we had computer-aided design, CAD programs. This happened in the 80s, late 80s. Why? Because computers are very good at being able to draw straight lines. It makes it easier. You can easily edit things. Another place where it was first computers were first used was with word processing. Why? Well, because with a typewriter, it's very difficult to edit what you have. You have to retype it from the beginning. Whereas with a word processor like Word, you can take things and you can move them around. Now, from those very humble and small beginnings, computers have moved on and they've infiltrated all kinds of places. So we have, computational biology, where computers are used, for instance, to mimic the way animals that may be extinct moved. And how does it do that? It figures out what the muscle mass was like, where the muscle attachments are on a particular bone, how the joint moves, how much it weighs. And then it does some math and it figures out, well, this is what it would look like moving. Computational chemistry, physics, mathematics, computer-aided design is here. Computer-aided manufacturing. We've all seen, well, most of us have seen pictures of factories where they have the robotic arm and it's either spray painting a car or it's putting something together. Those robotic arms are programmed by a piece of software that tells it what to do and when. Computational architecture, very similar to computer-aided design. Computational social science has to do with statistics and calculating statistics and drawing conclusions from those statistics by using a computer. Again, computers are great at number crunching. Computational journalism. Journalists use a computer to type things up. They use the internet to, so if they're in the field, they can type something up on a laptop and then they can send it to the publisher, and that goes either online or it goes into a newspaper or a magazine. Computational music, recording. You can record music and edit music and add effects on a computer. Computational photography, again, we use digital cameras, which are basically computers that take pictures. You can then use a computer to edit those images. So photography was also one of the first places where computers and computer programs were used. So anyway, these are various computer-related fields, and they have to do with using a computer. And by the way, we don't have to get this esoteric. Just go to a 7-Eleven or an AM/PM, and they're using a computer as a cash register most of the time, and they're using a computer in the back to keep track of inventory. And that's been going on for a very long time also. So having said that, let's move on to what is actually computation. So one way to explain computation is to use a method called algorithm or an algorithm. And so an algorithm is basically a series of steps that can be systematically followed for producing the answer to a certain type of problem. So what does that mean? Well, if I take the computer part away from it, this is problem solving. When I talked about the light not working when I turn it on, I then created a series of steps that will help me diagnose why the light isn't turning on. And typically, the steps should be well defined, and we tend to try the easiest ways first. with problem solving. So, like making sure it's plugged in is the first step. Why? Because that's super easy. I just look down here and see whether the cord is plugged into the wall. What's the next step? What's the next easiest thing to do? Well, I check to see whether the light bulb works. I wouldn't do it the other way around because check to see whether the light bulb works. You know, I have to take it out. I have to get a light bulb that I know that works. I have to screw it in, and then I have to test it, and then it works or it doesn't work. And then if it doesn't work, I go, huh. And then I check the wall, and then I realize that both light bulbs work. So that doesn't follow in a logical progression. Now, what are some characteristics of a good algorithm? Well, the steps should be clear. If we're talking about a computer algorithm, we should have well-defined inputs. That means what is the user going to input into the program? It should be, by the way, algorithms are not programming language dependent. So we're not even worried about programming anything yet. We should have clear answers or clear output. That we define what the output is going to be. With a problem solving thing, it could be that the lamp then works. That's our output. The steps should be easy to understand and should be clear and unambiguous. And by the way, the steps that we take should be feasible. And what does that mean? It means that the steps we take should be something that we can actually do. And, or easily do, or, well, I shouldn't say easily do, but shouldn't be so difficult that it's very hard to do it. And there should be an end. So that means that we need to limit via time how long it's going to take to get the answer or the output. So I don't want to check my lamp for 4 days in order to figure out why it doesn't work. It has to work in a reasonable amount of time. So